stuff. So again, we've been going through this unit in terms of starting at Earth and working our way out, right? We started at Earth, talked about its properties. We worked our way out to the satellites and the moon and talked about how they exist kind of in orbit. We worked our way out to the planets, talked about some of the properties of those and our solar system. And then we worked our way out beyond our solar system out to the nearest stars, traveling out now using the unit light years, which is that distance in which light travels within 1 year. And it is a great, huge distance. I think, if I recall from our lesson the last day, I believe the power of 10 on the back of that number was something like 10 to the 15 meters, I believe. It's a massive, massive distance. Okay. And then we said that our closest star was about 4.2 light years to our nearest neighbor. And then we talked about stars and how they evolve, not evolve, but how they exist in the main sequence, the way the sun burns, and then ultimately their final ending points, either a brown dwarf after it being a white dwarf, a neutron star if it's medium weight, or a black hole, which is the most strongest gravitational source in our known universe that can even pull light in, and therefore it is black. So as we zoom out of our universe, or zoom out of our point of view, we're going to now encounter a couple of different types of organizational groups that we need to label. The first thing that we're going to talk about still exists within our galaxy, all right? Now, maybe just a quick talk about what we mean by a galaxy. A galaxy is a very big structure made up of billions and billions and billions and billions of stars, all right? Our galaxy is called the Milky Way galaxy because of the way it appears in the sky when we look up at the night sky. And we'll talk tomorrow about how we can see our own galaxy even though we're in it, all right? We'll talk about that maybe even a little later on. But in the night sky, there's so many stars in that particular region that it looks like it's milk, almost, through like a rivery milk. So it's got an interesting look. You need the sky to be very dark in order to see this, but that's the way it kind of looks, and therefore it's been given that particular name. So we're still within our galaxy in our little trek here. So we want to talk about some big structures that are within our galaxy. Then we'll talk about the galaxy itself and other galaxies. And then we will zoom out one more time to encompass what we would consider to be the entire universe. In other words, everything that's within what we believe exists in all of space. All right, it sounds pretty grand, and it is. It's pretty cool. Okay, so let's first talk about star clusters. And again, I'm talking now within a galaxy. We haven't left the galaxy. We haven't left this big object. And again, we were talking about individual stars last day. So if we zoom out or step back our point of view, the next larger structure that we find are called star clusters. So groups of stars that tend to be close together in space. These clusters of stars can be formed in different ways. We're not worried about that. I'll come back and talk a little more about star clusters when we zoom out to look at the galaxies. Again, the larger structures. So they're groups of stars formed by the same nebula. They stay together again due to gravity, so we can have groups of stars hanging out with each other. Open clusters have no particular shape. They're just kind of random stars in the same area. Notice we're talking numbers of like 6, as long as they're kind of grouped together, to thousands. They can be thousands. So notice we're not talking about billions and billions and billions of stars. We're not to the galaxy level yet. And these tend to be young, the open, and then we have what are called globular clusters. I don't know if the word glob is a thing, and something, if something has the property of being glob, it becomes globular. But I guess that's it. And it tends to be this kind of packed group in the center with then more spreading out, more diffuse stars, and there tends to be many more. And notice I'm at thousands and 10 to the 6th. I decided to use some scientific notation there. Remember, that's 10 with 6 zeros, essentially millions, right? Thousands to millions of stars, kind of grouped together. So again, as we're stepping back from the smaller structures to larger and larger structures, after individual stars, we encounter a cluster of stars. All right? And we're not going to talk much more about that, other than that's the next larger grouping that we can talk about. Everybody have that down? I've been talking away. Looking good. All right, so we're going to continue to zoom out, and that then brings us to galaxies. So now we've zoomed way out. And we are talking about massive structures. With millions to hundreds of billions of stars. And we now know that many of those stars contain planets. So stars and planets and all kinds of things in there. They can be 100,000 light years across. Our galaxy is on that scale. We are in a fairly large galaxy. And they come in 4 categories, and I left it blank there because my next slides are going to describe the categories. So we've gone from the little clusters, and really the clusters are tiny now in terms of size as we've zoomed out to the galaxy itself with, I wouldn't even know how many clusters. There'd still probably be millions of clusters, right? With millions of clusters containing millions of stars, you're into billions of stars, right? You're into massive numbers, hundreds of billions. And their categories are determined by shape. Are we good to go? All right. So the first type is elliptical. You don't need necessarily to have a big name there. You could put it off to the side as a subheading under the different shapes. I just happen to use this type of slide as my main slide. You can just put it off to the side, maybe to the left, elliptical. And the reason I'm leaving some shape here is I want to draw some simple representation of these for your particular notes. They're spherical to flattened ovals, so they could be, they could be something like this. And again, I'm drawing it almost to look like an egg, and that's fine. That there's a brighter center with an outer edge, and these are all made up of stars in there, however you want to draw that in there, but it's got that spherical shape. Some of them are almost flattened ovals. If we looked at them on end, right, you'd have a circle and then you'd have another kind of piece there around it. These are all stars. I'm not drawing Saturn here, but I'm drawing massive numbers of stars. We're zoomed out by massive lengths to fit that in so we can see it. All right? How do we know these things exist? When we point the telescopes in certain directions, you can see these very far away, very big structures. All right? And I'll talk about how we know that they're very far away. So in this picture, these stars are within our galaxy. Here we're looking out past our galaxy, a massive great distance, to another galaxy that's very, very far away. So when we look at these in the sky, we're looking out to great, great distances. Okay? All right? Elliptical. Not exciting. Next, spiral. I didn't leave enough room there, but I'm going to draw both of them. A flattened disc with a central bulge and spiral arms. So they have these kind of, almost looks like areas where there seems to be lots of stars in this area. We've got this massive center, and then we've got these kind of areas where there's lots and lots of stars. And so how am I going to draw that? I'm going to draw that just as a central area there, again, made up of many, many stars, probably a black hole in the center there, a huge one. And then, and again, they're all made up of stars. And then I'm going to draw just kind of these spirally things as if it's a spider that's struggling in some way. All right. And each of those arms are made up of, again, millions of stars. Some are obviously much brighter than others. Some of these could be stars from our galaxy as well, with that being way out there a great distance. But you get the idea. Okay? A barred spiral has the part in the middle, but it seems to have this kind of non-spirally part, like a bar, almost like it's an elliptical with arms. So if I'm going to draw that, I'm going to draw the circle with the kind of the bars. Again, that's all made up of stars. And then off of the bars, I'm going to put the spirals. I'll put it in the same direction as this one just to make reference. So you'd have a spiral right like that, and a spiral like that. And then there is some other spirals that come off of it, but that's good enough. So it's got this bar in the middle with the spirals coming off of the center. Okay? Our galaxy is a barred spiral galaxy. All right? It has that bar in the middle. It's a smaller one, but it does. Okay? So the shapes are defining it. In this textbook, and I looked back at the galaxies, there's even subdivisions within these. So if you really wanted to get into astronomy, you can look at even more subdivisions of these types of things. We're just getting you guys the basics. Okay? We're all right with spiral. And a lenticular, and I don't know where the term comes from, a large flat disc with a central bulge, no spiral arms. I kind of have that over on the elliptical as well, but again, it's like a really big barred spiral without any arms. So that's got lots of stars in it. I'm kind of looking at it edge on, right? There you can see there's some dust in there that's absorbing some of that light. But there are no spiral arms, older red stars. Okay. Not exciting. And again, all of my dots in there are representing billions and billions and billions of stars is the idea. Okay? Yep. Yep. We're good to go? Good to go again. This is not super exciting at this point. We're just talking about what things kind of look like. And there are irregular galaxies. And I'm not even going to draw one of those. They have no definite shape. They tend to have more gas. Maybe they're young. I really don't know. Again, I'm speculating. Maybe they haven't had enough time to have gravity get everything kind of in order and spiraling in towards it. I'm thinking if I were to, dig into this book, I could find that out, but again, it's not a concern for you at this point, and I don't think we need to worry about it. But they're irregular in shape. We do have ways as scientists to see the gas. Even though the gas might not be luminous, it might not be giving off light, right? We're probably just seeing the stars here, but we can tell that there's gas there, again, by looking at the color signature for hydrogen. I talked a little bit about the color signature. We'll talk a little bit more later, but we can see those gas, we can see the gas and the way it moves by looking for a particular radio wave, and that indicates to us whether there's a lot of gas or not. So if we look at these galaxies with light other than our visible light, but other light that we can measure, and one is radio waves, then we can see that there's a lot of gas there. How are we doing? Good. All right, so let's talk a little bit about our own galaxy. So our own galaxy is called the Milky Way. It's about 10,000 light years in diameter. This is a conceptual image. There is no way that we could send a space probe into that position to take that picture. So it's what we believe exists based on what we can see from our point of view. Okay? Again, I'm going to draw a little representation of this based on that picture that we've got there. So there's our barred center. And then we've got, again, spirals coming off. I'm going to go counterclockwise in this case. So we've got spirals coming off, all kinds of different spirals heading out like that. All right? It's not a big deal. And our sun is about halfway out from the center. So if you wanted to put a label here, you could say right about there, there is the sun. Again, it's based on what we can see from our point of view using various types of telescopes. Tomorrow we'll talk a little bit about telescopes, because tomorrow we're going to talk about what we see in the sky. From our point of view on Earth, our Earth is tilted with respect to this flat part of the galaxy because it's a flat disk. And at night, if it's really dark, you can see this area that cuts across the sky that has lots and lots and lots of little tiny stars. And that's us looking edgewise out at the spirals. Okay? All right? I believe, I'm not 100% sure of this, but I believe when we have a good view of it, we tend to be looking away from the central bulge. We're not looking towards the center. We're looking away for some reason, and I don't know why we can't look towards. I think we're looking away. Does the southern hemisphere maybe look towards the bulge? I'm not sure. It could be that that's the case. I thought I'd read that once, but I should check that out. But we're looking edgewise, all right? How do we know that this is the shape? Again, for each of those stars that we can see and we can study, we can determine a distance. I'm not going to explain how, it's too complex, but we can. And so from our point of view and knowing those distances, then scientists can create a plot of where things are, right, out from what we're looking at, and we get this view of this. All right? Again, it's a It's a theory based on what we can see. It's not just a theory. We do have good observations. I have seen a report just as recent as last year that some now believe that on the outer edges, there's a little wisp to it. There's a little twist. One side twists down and the other side twists up based on some new observations. So our view of our galaxy changes as we get more data. Yep. The thing in the middle is the supermassive black hole. That's what we believe to be there. All right? It's producing light because these poor stars that are existing, or this poor matter that's existing in this space, is falling very quickly towards the center, and as that happens, there's all kinds of action that takes place that causes things to spiral and charges to give off light, so it gives off light as it crashes in.
So we're being sucked into a black hole.
Very slowly, we are being sucked into a black hole. Yeah. Yeah. Now, there's all kinds of, again, different theories about this. We should be, according to the math, we should be spiraling in faster than we are. There are many galaxies that are not behaving the way they should be based on laws of gravity. So this is where scientists propose that there might be some other material out there, maybe beyond here that we can't see, that is causing the galaxies to behave differently than the way we think they should. And we call this type of stuff dark matter. I don't know if you've ever heard of any of that, if you've read anything. So, well, I'm not talking science fiction dark matter. But it is a theory that there must be something out there that's preventing things from moving the way we think they should. But that's right on the edge of new physics and new science. Again, different stories come out in different reports. Nope, someone did some new math. We don't need dark matter. We can explain it a different way. So we're talking really right on the edge of what we're learning, right? So I'm not going to have you write down anything about dark matter. I think it mentions something in your textbook, but I'm not even going to worry about that because it's still kind of a question mark thing. Yep. Well, we've got to worry about our sun becoming a red giant in about 5 billion years. So if we can beat this global warming rap, all right, then and we can coexist on Earth without completely bombing each other into oblivion, and we can manage to get to 5 billion years, then the end of the sun's life would probably be our next biggest problem before we have to worry about falling into the black hole.
What if black hole moves?
Well, let's think about that. That's actually, I know Jay is being Jay, but we can. You're wanting to. Well, anyway, let's not worry about that comment. Let's think about this for a moment. Is the Earth moving right now?
Yes.
Yes, it is. Are we feeling its effects? No, not really. We're flying through space right now, but we're just kind of going along for the ride, right? Why do we just go along for the ride, and why don't we just all get flung into space as the Earth takes off around on us? That'd be, wow, everybody's getting sucked into space. Why not? Yep. Gravity is keeping us there, okay? So as the Earth moves, we move. Same with the moon. The moon is moving with us. Why doesn't the moon get flung off into space? Gravity, right? So let's change this particular point of view. Is the sun moving? Any ideas? Is the sun moving? It is. The sun is in orbit around the center of the galaxy itself. Okay? So we're moving on Earth, which is actually moving with the sun, right? So here's the sun, and that sun is in orbit. I don't know the direction, but let's say that sun is in orbit in that direction. Is our planet being flung off of the sun due to its motion? Why not? Same answer. What keeps us moving with the sun? Yep. Gravity keeps us moving with the sun. Okay? Gravity does. Now, there's actually another galaxy that's fairly close to us. And I think it's called the Andromeda Galaxy. And physicists predict that in some time in the future, the two galaxies will collide and create one great big mess. Because the two big black holes that are in there are going to come together, and stars and matter is going to be flung all over the place. In actual fact, it's believed that we're already moving in a trajectory that will automatically have us run into that other galaxy. Okay, are you following along? That means that our supermassive black hole, just for the sake of argument, is moving. It is moving. You said, what if it moves? It is moving. Are we, the sun, being flung off into space? Why not?
Because we're being sucked into a black hole.
Yep. We're orbiting the black hole, and the gravity is keeping us in place. In other words, we're going along for the ride. The black hole would orbit the center of mass of those two galaxies that are doing this dance. You see what I'm saying? They're kind of spiraling together. There's going to be a point in the middle where those two things are going around the center. All right? You see what I'm saying? They're kind of going around the center. I'm trying to think of an example of how to have you visualize this. But when you flush the toilet, everything goes kind of around the center there before it. You see where I'm heading with it? You know what I'm talking about? Anyway, it's not the same thing, but it's the same idea. Yes? Yep. Okay, here, I'm going to just advance to this next slide. So you said there's nothing more massive than a black hole, so what are they orbiting, right? Is that what you were asking? Is that what you're asking? So these are great questions. And these are questions that are right to the edge of what we know from our observations. It gets us to the outer limits of what we know. You can have different sized black holes, all right? In our galaxy, and I've already advanced it, in our galaxies there are small black holes that are not in the center, and they're also orbiting the center of the supermassive black hole in our galaxy, okay? So in our galaxy there are existing smaller black holes that go around just like our sun and are doing its thing, being drawn into that supermassive black hole, okay? So now we zoom out to what's called the local group. We also know, based on distance measurements, and I'm going to talk a little bit about how we measure distances, that there's a little group of galaxies that the Milky Way is hanging out with the Andromeda galaxy being that one that we seem to be running into, okay? Now at this point, we don't necessarily need to have a black hole here because they will do this kind of binary dance, this movement around each other that they will orbit around this central point, all right? Okay? You guys are asking really good questions. You don't have to have that central part. How can I show you this? Oh, okay, let's see. Mr. Petrus has the tools, so I can't get a hammer. I'm looking for a hammer. Yeah. In your backpack? You have a hammer in your backpack? In your locker? It's okay. Let me get to the end of the lesson and then I'll try to come back with this. The key is the key is you don't need to have one object bigger than the other in order to orbit around. When we talk about the moon going around the Earth, right, we assume that the Earth is standing still, but in actual fact it doesn't. It wobbles as the moon comes around to the other side. In reality, both orbiting objects move, right? The moon orbits the Earth, but the Earth does a little wobble orbit of its own, just a little wobble in space. But because the Earth is so big, it hardly moves, all right? If we had two objects that were the same size orbiting each other, they would orbit a spot right in the middle. They'd go around like that. As one gets bigger, the smaller one gets flung around and the bigger one doesn't move as much. In this case, they would orbit around a center location. Yep. Yeah, that's a good question. Let me get to the end of this and I'll come back and talk about it. Yep.
Okay. Honestly, when you really think about it, seems that like the entire universe and world really ending, like nothing. Actually, like no more humans, no more chipmunks, no more.
You mean the entire universe just disappearing? Just like disappearing for no reason?
No, we just going back from
If something were to go into a black hole, is that what you're saying?
So just think about the entire world ending. No more human life.
But why?
No more.
But why? I'm not saying why do we not want to think about it. I'm saying what's causing it. Something has to cause the end world. You got one statement to make before I move on. You better make it a good one. What's causing it? The black hole? We'll talk about that later on. Once I get to the end of this, we'll talk about what would happen if we fell into a black hole. If she wants to entertain that. Yes. Hey, have we wrote this down? Excellent.
Say we take the sun, we put it in a bottle.
Nope, not doing that. Not doing that. Yep. Yes. You can have two black holes collide. Their masses would combine. They would become a larger black hole. Correct. Yeah. No, there wouldn't. Their gravity wells. Remember when I had that big thing? It would just become a bigger, steeper hole in space that things would then fall into. It would simply get larger. Now, for some reason, scientists believe that there was a certain extent to how big they could get, but I've recently read some abstracts of some reports of scientists now. They're seeing super massive black holes, these massive things that we can't explain, but they've got like massive size. So there's still more science to be done. You're on a short leash. Go ahead. Start.
Okay.
Be prepared to shut down.
So say if the sun falls into a black hole and then it dies, will it cause a black hole inside the black hole?
No. This black hole will just get bigger. Yep.
If there's like a super huge black hole, could there be galaxies orbiting that black hole?
Sure there could. Like maybe out in empty space in that local group? Sure there could. Sure there could. I've never heard of any type of object being discussed. But you're saying some great big massive black hole that was formed by multiple galaxies or something? I believe that the physics would be okay with that, but I've never heard of an object. That's why you'll notice I haven't even mentioned it. You know what I mean? So I've never heard of such an object. Yeah. In my textbook, theory can calculate the edge of where light can't escape. It's called the event horizon, all right? Anything inside that event horizon will never escape. Anything on the outside of the event horizon has got to go almost the speed of light to escape. So light can just barely escape. There's a mathematical equation that determines the radius or diameter of that event horizon, and it depends on the mass. The greater the amount of mass that has fallen into that black hole, the larger the event horizon is. So the black hole's radius, where light can't escape, does get bigger as more massive it becomes. It doesn't get smaller and bigger. The sphere of its influence on the light gets bigger. So the point of no return for the black hole gets larger as more mass falls in. It's like it's now able to encompass more space. So it gets bigger. Yeah. Okay? All right. That's for neutron stars. I said that it gets smaller, right? That's for neutron stars. Once the neutron star gets so small that it collapses and becomes a black hole, then there's this new edge where light can't escape, and that's what we define as the edge of the black hole. It isn't a thing, all right? The edge of the black hole that I'm describing, this event horizon, isn't a surface like a planet. It's simply an artificial line in space that if anything ends up inside that, it's falling forever to the center. Okay? All right. Let's now then talk about the universe itself, the largest possible structure that we can encounter. That means there's lots of galaxies, etc., etc. So again, we've seen that there are actually millions and millions and millions of galaxies, all right, that exist in what we can see as space, all right? And it turns out that these galaxies are all moving away from us. They're all simultaneously moving away from us. And the further they are away, the faster they move away from us, all right? So what this means is the universe is getting bigger. The universe is expanding. It's growing, all right? That's kind of exciting. The way we know that the universe is growing has to do with something called redshift, and you're going to read a little bit for homework, but I'm going to describe it briefly, all right? If we were to have a flashlight, all right, that we could then turn on, say, from a galaxy and shine some light towards us, that wave would travel through space to our eyes, and we would see it, okay? But because this galaxy, try to do a barred galaxy here, because this galaxy is moving away as it produces the light wave gets stretched out because it's moving away from us. So instead of the light wave looking like this, the light wave has now been stretched out before it gets to our eyes. The wave gets longer, okay? When light waves get longer, they become redder in color. So, when we look at galaxies far away, we see that their light has become stretched or has become redder than it should be. And the further away we look, Hubble did, the further away he looked at farther galaxies, the more red it became, which means the further ones are moving away from us faster. The universe is growing, all right? Based on these observations on the reddening of the light and the fact that the universe is stretching out, a scientist, and I have no idea whose name this guy is, said, what if we run the clock in reverse? If we run the clock in reverse, it means that the universe gets smaller and smaller and smaller and smaller. Based on what we know as the current size and based on turning the speed in reverse, we get to a point where the universe started as a tiny little thing. And if it started as a tiny little thing, all of that mass had to have been in that tiny little space. And therefore, in order for our universe to exist the way we see it and run the clock forward, then that tiny little material, whatever it is, well, not tiny, but all the material in the universe squeezed into a tiny spot, had to have pushed out for some reason, hence the bang. And that's the idea of the Big Bang theory, that there was a big bang at some point in our universe's past that then pushed all matter out in all directions to the point where we exist now and we're seeing the universe go off in all directions. All right? Yes. Yep. Fire away. Ah, nice. Yeah, and do you have us to follow up with it?
No, it's a bit different.
It's a bit different. Okay. I'm going to bring this up so that you can write it down. And let's now talk about what's the center of the universe. I knew you were going to ask this question. You're in your mind, which you're correct. You're saying, Mr. Sanders, if you're saying that we're seeing all of the galaxies moving away from us, then we must be in the center of the universe. Because if everything's expanding away from us, when we look in all directions, and you run the clock in reverse, then that little tiny spot has to be here, where we are. And you know what? You'd be right. Now, we could go off to another galaxy where perhaps aliens exist. And these aliens would look out into space and they would see the same thing. They would see all of the galaxies moving away from them, faster, further away, even though we're the far away ones. And they would say, we're at the center of the universe. How awesome that is. It doesn't matter where you are in the universe, you would see the same thing. How do we explain that? Now, I am going to wait for everyone to finish writing that, and then I'm going to explain this. You have an answer? Oh, well, I want to explain why we see that we're at the center of the universe. What do you got?
Would it be that we're moving as well, so everything's moving?
Ooh, so that everybody's kind of moving along with it? No, there is another explanation, but that's not a bad idea. Do you have another question that you want to add on to that one? Okay, keep going. Yep, is that reverse and then energy coming out? Yep. Yep. You can. With high enough energy, you can produce matter and antimatter. So you can create and destroy matter. You just have to have it. It's got to come from energy. It's got to come from light energy, and that is Einstein's relativity theory. That is E equals mc squared, right? And that's something I've not mentioned yet in this course. But there is an equation that allows matter to come from pure energy. So we now know that instead of it being matter there was some high energy source that then became matter and antimatter. So we do have theories that can explain that. We do. All right? Let me go with why we see things going away. Okay, so we exist in 3 dimensions. Are we okay with that? We are tall, we're wide, and we're thick. Okay, which means we have length and height and depth, right? But that doesn't mean that there couldn't be more dimensions that exist in nature. There could be a 4th dimension, a 4th spatial dimension that we cannot sense with our brains and our eyes. Let me change the scenario for you. Let's imagine instead of us being able to live in 3 dimensions, we were beings that could only exist in 2 dimensions. We exist on paper. Okay? We can't actually physically exist in 2 dimensions because we are beings that need to take food in, and we need to digest food, and we need to excrete food. And if we lived in 2 dimensions, it means our food tube would cut us in half. Think about it. If we were flat on a board, like on the chalkboard, and we were drawing ourselves and having a digestive system, that digestive system would result in us falling into 2 pieces. So this obviously can't exist. But let's imagine it. We live on a flat land. And let's say, right, Allie is the first intergalactic spacefarer going off, NASA, congratulations. And she's going to head off into space to find whatever she can find. 5-year mission, Star Trek? No? Anyway, that's fun. And she takes off in her spaceship and she goes for years and years and years. Jenna is wondering what's going on. She's getting old. She's wondering what's happening. And after many, many years, Allie comes from the opposite direction and comes back home. And we say, what did you do? How did you get over there? Did you turn around? No, I kept flying in one direction. What happens? How can we explain that? Instead of us living on a flat piece of paper like we thought, we actually lived in a 3-dimensional space on the surface of a ball. But we don't have knowledge of that because we can't sense 3 dimensions. We can only sense 2 dimensions. So the universe that we thought that was flat was actually curved in a third dimension that we cannot sense. So when Allie flew off in one direction, which we thought was straight out in space, she went around the third dimension of the ball and came back to the same location. Which means, if we can only sense 3 dimensions, then why can't there be a 4th dimension curve, some kind of 4th dimension ball? Are you okay, Robert? Or am I blowing your mind? I just blew his mind. There was a little explosion there in his mind, but he's this is an epiphany. And that means if you were to truly fly off in our 4-dimensional space, you'd come back from the other way. Now, there's no way in which that can actually happen, because it turns out that the expansion of the universe is greater than the fastest speed that we could ever go, the speed of light. So there's no way for you to actually do that. It'd be really cool and really awesome. So then why is it then that we're seeing the stars and the galaxies going away from us in all directions? Well, if this is my 2-dimensional world, right? You're going off to space. Woo! Yeah, welcome back. Dana, 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 party, party. All that type of stuff because you made it back. So if we are existing, now I'm losing my, I only needed my Sharpie marker once today and I lost it. If we're existing right here, big X because we're super important, right? There we are. That's us. And we see stars that are all over the place there, maybe some galaxies way out there, some galaxies and everything. All right, and again, we're right there in the middle. Oh, that's terrible. Look at that. We're on some jagged-looking planet-type thing. As the universe grows, everything spreads out in the same direction. It spreads out the same if I live here, or if I live here, or if I live here, and we see everything heading off in the same direction. This is the only geometry that can explain what we see. This is the only geometry, because our place in space isn't that special. We're off on a sidearm of a spiral galaxy, all right? Yes?
So, if we already have discovered all of this knowledge about the previous
Yep.
here,
Yep.
why are there still people who believe the Earth is flat?
Oh, goodness. Well, that's a... Oh, there's not scientists who believe that. Not real scientists. That the Earth is flat? No, you're reading something goofy on the internet about scientists that think that the Earth is flat. Okay, in the past, the universe started as an explosion of a hot, dense, very small gas about 14 billion years ago. That's just running the clock backwards, all right? This would be the beginning of time. The young universe expanded and cooled quickly. How do we know what we're seeing? Well, this is an interesting picture. The expansion, they believe, was very quick at the beginning. Light could not escape until it got to a particular size, and then light could start to travel. That's exactly the same as the light walking around in the sun. Remember I talked about the random walk of the light in the sun? The universe was so dense in the past that the light couldn't escape or travel because there was so much matter packed into one spot. And then once we got to a large enough universe where the matter was spread out, then light could take off. Matter started to clump up, form galaxies, clumping to the point where we are today. Yes?
So, everything was created by, like, a piece of mass that we met?
We're not sure if there was actually matter there or not. It could have been just energy. Some scientists believe that supermassive black holes that have all this mass falling into them, where does the mass go? Some think that bang on the back end of that black hole in the 4th dimension, another universe spits that energy out the back end. Maybe a black hole from another universe that's right up beside us. Well, maybe from a black hole from another universe that was beside it. Well, that's kind of, at this point, we're into the idea part. Please write this down. And by the way, microwave background radiation is not your brain getting fried by looking at the microwave oven. That's not what I'm talking about here. So don't go home and say, Mr. Sanders says don't look in the microwave. That's not what this is. You were going to do it, weren't you? Yes.
So, like, going back to the black hole.
Yep. Yep.
If it just goes on and on and on, there's no
Ooh,
beginning.
you're right. You're right. You're right.
A thing.
You're right. I'm not telling you that I believe that. I'm not telling you that I believe that.
But if there's no beginning, then there can be no.
You're right. You're right. That's right. And you know what? I don't. These are ideas. What I'm telling you are just ideas at this point. Running the clock backwards, we know the physics pretty good. It had to start from something. But we're not sure what that before was. What I'm throwing at you here about, black holes spitting its material, these are ideas. These are really, truly pie-in-the-sky ideas of scientists. But that's what scientists do. They brainstorm. They try to think, can we explain that? So I'm not diminishing our discussion that we had earlier on. I'm not at all, because I'm not necessarily believing that either, but that's ideas. I'm just saying it. You know what I mean? I wouldn't sweat over it. What's that?
What's the beginning idea, though?
Well, I don't, at that point, if we go with the black holes, just keep doing its thing, what's the beginning idea? Well, if you really want that, something, right, had to put this structure in place to make the machine run. There had to be something that created this machine that appeared to be in. That's where I put it. You see what I'm saying? You see? There had to be something or someone that put that machine into being. Anyway, okay. When we look out into the sky with a telescope that looks at a particular color of light, which is a very cold temperature, we see this structure. We believe this to be kind of the map of that original Big Bang. Again, it's called microwave background radiation. We believe it to be the heat that's left over from that big explosion. That's one of the reasons we think that it exists, because we see these little dark and light spots in the temperature of empty space where we believe that there were some hot spots after the Big Bang. That's called microwave background radiation. Okay, again, we can see it in all directions, just like we can see the expansion in all directions. Do we have that written down? I'm down to my last one. Yes.
Like different black holes beside
Yep.
each other. Is that where the multiverse came from?
You were loving this reference to your comic books, right? There is a theory of multiple universes existing. And again, these are ideas, right? Not necessarily. We have other theories that talk about how we can have that extra fourth dimension, you know what I mean? But if there's all these extra dimensions, then we could stack all of these universes up really close together in another dimension, and that's really this multiverse idea than the black hole thing. But there is definitely a multiverse idea out there. But again, these are theorists right on the edge of ideas. They're brainstorming. Okay. So how about the future of our universe? Let's not worry about where it came from or who built it or that type of thing. What's happening in the future? Well, we could have what we would consider a flat universe, but we're pretty sure that that's not the case. Because I described to you a universe that has this fourth dimension curvature, which is just fun. We believe more that it is a closed universe, that it does have a fourth dimension edge, like a ball or like a beach ball or something, okay? So then what would be happening to that beach ball? Well, it could be open. It means that it's going to expand and get bigger and bigger forever and ever, things just spreading out, which means in the end, after all of the black holes have won the battle, that there's just a very thin universe with some black holes floating around, and that's it. That's the end of it. The lights go out, all right? It could be flat. Flat means that it goes, but it slows down. And it slows down to the point where it gets to a particular size in that fourth dimension, and it stops. And again, black holes might come along and do its thing, and stars will be formed until the energy runs out. And again, it doesn't grow infinitely, but it still dies out and things get cold, and then the end is the end. But then there's an also idea that it's closed. It's believed that if there's enough mass in the universe, that gravity could win and pull everything back in again. So it's going out, the ball's getting bigger and bigger, but gravity's going to win, and the ball stops and then comes back in and brings all the matter closer and closer together, hotter and hotter and hotter, and then all that matter gets squished back in to a massive black hole, where then maybe you could have another Big Bang, and the machine runs again. They call that the big crunch. It all comes back together, and the machine fires up again, and the universe starts again, things flying off in all directions. Again, these are just ideas based on what we see. They do have ways of kind of calculating this. If there's lots of mass in the universe, they think it's going to be closed. If there's not enough mass in the universe, it's going to spread out and it's going to be nothing. Cold, darkness. Not exciting. Again, if it's flat, again, cold darkness, but it's just not growing anymore. These, again, are just cutting edge kind of ideas. Okay. That's the end of my talk. Oh, aliens, aliens. Please write this little thing down. You've got one little bit of homework on redshift. I talked about it. I want you to read the section on redshift on page 394 and answer number 1 on page 397. Aliens. Aliens. Am I going to record my discussion on aliens? Aliens. We do. Right at the very back of my big astronomy textbook. In actual fact, my astronomy textbook talks about life on Earth and the probability and what had to go through in order to get life on Earth. So then the textbook talks about estimates for the number of advanced civilizations in our galaxy, not even including galaxies far, far away. Well, I've been waiting a long time for that one. I've been waiting a long time. So let's just stay with our galaxy. Anyway, let us now return to our original question. How many advanced civilizations might there be in the galaxy? To begin a rational discussion of this point, we must adopt certain assumptions. In other words, we've got to make some guesses. Let me keep reading this for a moment. The most common hypothesis is that all intelligent life forms, whatever their present shape or nature might be now, had an original chemical process occurring on the planet orbiting some star. So we have to assume that all life is going to form similar to ours on a planet that's in the nice spot away from the star, right? What we call the Goldilocks zone. This is, okay, this is, of course, a conservative assumption modeled after our own example, the Earth. Okay. Adopting the conservative assumption outlined above, Frank Drake has proposed that the number of advanced civilizations in our galaxy with whom we might make contact is given by the formula. Don't worry about the formula. L is the average lifetime of the civilization when they have enough technology to send us information. So we've got to assume that this thing has enough technology to talk to us. R is the average rate of forming stars in the galaxy. So it depends on how quickly stars are formed, okay? Because if stars are going to create planets, and planets are going to create life, then we need to know how many stars are being formed. And there's a lot of them. And P is a number given by the product. So now we've got some things that we've got to assume. The average fraction of stars that have planets. It turns out that more stars have more planets than we thought. There's a lot of planets out there. The average Earth-like planets, in other words, ones that are in the good sweet spot, all right? Depends on what fraction they have there. Average Earth-like planets that have developed life. So were the conditions proper for developing life? The average fraction of life-bearing planets which have evolved at least one intelligent species. So we've got to have an intelligent species, not just, amoeba and bacteria. And the average fraction of the intelligent-bearing planets that are capable of interstellar communications. They must have intelligent species that can then create a radio or something to talk to us. These are all fractions. These fractions could be incredibly small. They could be something like 0.000001, all right, percent. But when you take into account that there are billions and billions and billions and billions and billions of stars, which we now know contain mostly planets, and we're discovering as we look at those stars, Earth-like planets, all there needs to be is that water for enough time, right, to then advance life, okay? Because the numbers are so big, I believe that there is life on other planets. Is there intelligent life that can talk to us or send people to us or measure, or you know what I mean, or get our attention? That's a different story. You see what I'm saying? That's the hard part of the question. Is there intelligent life? And how would they talk? And would they communicate with us, et cetera, et cetera? But I believe due to the vast numbers, dealing with the numbers of stars and planets, even if the probability is low, that there are other life-bearing celestial objects in our galaxy. Whether someone's going to send us a wave or send us a message, that's hard to say. Yeah. Yep. Don't worry about it at this point. Don't worry about it. I was doing some checking of some homework, but don't worry about it. This is just one quick question to kind of summarize it. Yep.
Second question, like you said, like is there, or like intelligent?
Yep. Life